So welcome everybody, and it's a great pleasure to have Edward Laird giving our talk today. Edward is a lecturer in experimental condensed matter physics at Lancaster University and a member of the low temperature physics and quantum nanotechnology groups. Following an undergraduate degree at Oxford University, he did a PhD at Harvard University working on spin qubits in semiconductor quantum dots. And he was then a postdoc at Delft University of Technology, where he developed qubit and mechanical devices based on carbon nanotubes. And then after an RANG research fellowship at Oxford, he moved to Lancaster in 2018. And his research focuses quantum electronics in nanoscale devices. And it's a great pleasure to hand over to you, Edward, and we look forward to hearing your talk.
Thank you very much, Gavin. Thank you for that kind introduction and for the invitation. Let me share my screen again. Okay, so I'm going to give a talk about nanomechanics with vibrating carbon nanotubes. And since I know that you have a big interest in this seminar in quantum collapse and in how large quantum superposition can be, I will include in this talk a large amount of theory, and in particular our proposal for an experiment that we call the displacement, which is an approach towards testing quantum interference using a tethered vibrating carbon nanotube. Let me start by acknowledging all the people who've helped me. This is my new lab in Lancaster. Most of the experiments that I will talk about were done in Oxford with collaborations with contributions from other places. The two people I particularly want to thank are Yutian Wen, who was my PhD student in Oxford, who led the experimental work that I will talk about, and Kieran Kosler, who is now a postdoc at Imperial College, and was the lead author on the theory part that I will talk about. So why am I interested in nanomechanics? Well, there's two reasons. There's firstly that this really interesting fundamental ability that it gives you to explore how quantum mechanics affects mesoscopic and macroscopic devices. But also there's a very large practical value as well, which is that it lets you approach the limits of force sensing. And this is important. I mean, it's fascinating by itself, just the technical challenges and how you overcome them. But it's also potentially really useful. So in an atomic force microscope, then what you have is some kind of mechanical cantilever that scans over a surface. And by looking at the deflection of this cantilever, you can measure the force that the surface is applying and therefore work out what it's made of and image proteins and things like this. And the reason that there's still lots of room for new physics here is that it's a great challenge to make these sensors as sensitive as they can be. And a small enough mechanical sensor is limited by its Brownian motion, which is that whatever environment it's in, there will be some force noise on it that just comes from thermodynamics. And a room temperature atomic force microscope that you just buy off a commercial manufacturer at the moment has a force sensitivity that's around a piconewton, or piconewton per root hertz typically. And as you make them colder, you can make them much better. And by making them smaller as well and more compliant, you can make them better. And it's a great challenge to be able to measure the Brownian motion even at the lowest temperatures, but some people can do it. And with a carbon nanotube, which is about the smallest, lightest resonator that one can make, the force record, which does not come from me, it comes from Adrian Bachtol's group in Barcelona, is to measure zeptonewton forces. And that opens up all kinds of exciting possibilities, such as being able to image magnetic nuclei by looking at the deflection that they exert on some suspended nanomagnet. So the vision, if we can make nanomechanical devices that are sensitive enough that you could scan them over a surface and make magnetic resonance images of viruses or tangles of proteins in people's brains with isotopic resolution, and perhaps even one day with single nuclear resolution. So that's a very exciting, but very far off distant goal. And both in the fundamental physics that I will talk about and in this kind of application, then you have to make the right kind of resonator and be able to measure it with great sensitivity as well. And if your resonator is tethered, then you have an enormous variety of devices to choose from, which span an enormous range of sizes. This is a famous figure from an excellent review article by Aspelmeyer and colleagues. The domain of optomechanics spans all the way from macroscopic mirrors used in the LIGO experiment right down to nanorods or nanotubes inside an optical or an electromagnetic cavity. And then, of course, you can go one step further if you're willing to go away from having something that's tethered or clamped. Then you can measure cold atoms, levitated, or nanoparticles or, that are levitated or being dropped. And this also lets you do all kinds of exciting things. But what I'm going to be talking about is something that spans toward the bottom of this image here, so somewhere between nanorods and cold atoms, which is vibrating nanotubes, which are about the smallest and lightest resonators that one can make. So with any kind of mechanics experiment, you have the choice of whether you want to have a tethered resonator versus a particle in a vacuum. If you have a particle in a vacuum, then you can either levitate it and isolate it that way, or you can drop it using a drop tower if you're prepared for your experiment to have a very short lifetime. The advantages of tethered resonators are it's much easier to get a large mass because it's supported by the tethers, obviously. The frequency is pretty high because the restoring force is large. You have less significant problems of cooling because any heat in the particle is removed via the tether that's holding it, and you can integrate it into a circuit, and then sometimes it's more resilient as well. However, the price you pay is that the particle, your resonator is often poorly isolated from its environment because noise from the tether exerts forces on it. You can't let the wave function spread out because the tether pulls it back, and it's harder to use the tools of quantum optics. And there are lots of really exciting proposals for doing fundamental experiments using particles in vacuum. What I'm going to lead up to in the second half of this talk is about a proposal to test quantum interference with a tethered resonator instead. So this is the outline of the talk. The first half will be an experimental talk, and the second part will be theoretical. So the first part, I think, is going to give you an overview of what we can do, which at the moment is that we can measure classical coherence in a vibrating nanotube. And we do that by making fast and sensitive mechanical measurements using dedicated electronics at low temperature. And what we observe is self-sustained coherent oscillations. And I'll explain exactly what that means. And the proposal is that we can take the same kind of device, and by adding an extra ingredient, which is a superconducting qubit, we can realize a diffraction grating and therefore, at least in principle, test quantum interference with an entire nanotube, so the center of mass motion of a million nuclei or more. Okay, this is the kind of device that we measure. So what we're working always within this talk is vibrating carbon nanotubes. And you can think of these as being like little guitar strings. So this is a cartoon. Here's a nanotube. And you can think of it, if you like, as being a rolled up sheet of graphene. Maybe it's 1 or 2 sheets of carbon atoms thick. It has a diameter, typically of a few nanometers, and a length of a few hundred nanometers. And if you can make it so that it's held both sides, then on both ends, it's clamped by van der Waals forces to the pillars that it's supported on. But if the middle part is unclamped, then it'll vibrate. And that's what I mean when I say it's like a guitar string. And we can measure it. So the nanotube is generally, it's a narrow bandgap semiconductor. So if we have metal on the two sides, these green blobs, these green squares here, then we can attach wires to that. And to measure the motion, then we source a voltage, and then we measure the current that flows through the nanotube. And if the current depends on the displacement, then when the nanotube moves, the current changes, and we can detect that. Now, we also want to be able to control it. So to do that, then we use electrostatic gates that we put underneath the nanotube in this trench here. And using those, we can do different things. So if we apply a static voltage, a DC voltage, to the gates, then what that does is it applies an electrostatic force to the nanotube and pulls it down a little bit. And this means that we can control the frequency. So just like when you increase the tension on a guitar string, the frequency goes up. When you increase the static voltage, the frequency of the vibrating nanotube goes up as well. And we can also excite it. So if instead of applying a static voltage, we apply an oscillating voltage, if we hit the frequency of the mechanical resonance, then that excites the motion, and we can see that in the current. And then what we can also do is, even apart from the mechanics, because this device, like I said, is a semiconductor, then we can dope it. So we can switch different parts of the nanotube from being conducting to being insulating, and control the electrical potential that any electron moving through the nanotube sees. So we can create tunnel barriers and things like that. So that's what the device looks like in principle. This is an image of one that we actually made. This is from my postdoc in Delft. It's a few years old by now, but we're still making fairly similar devices. So the green here, this blobbly metal that got a bit damaged by some of the fabrication processing. That's the contacts. Here's the trench that you can see here. I've highlighted the gates, which you can only just see in the original image, but they're there, and you can see them in yellow. And the nanotube itself is this very fine string here, and this is the mechanics of this is what we're studying. And these devices, I learned how to make these from my colleagues in Delft back then. And the reason that they're still interesting is firstly that they are really beautiful, clean devices if you make them properly. So both electrically and mechanically, the disorder is low. So we know that electrically because we have a fairly smooth electrical potential, and we know it mechanically because the quality factor can be very high for something with such a large surface area. And this image here is not mine, but it's a transmission electron microscope from a former colleague of mine. And this is a nanotube. It's not a nanotube in a device. It's a nanotube made, synthesized chemically. But what it shows is that when we draw these cylinders of graphene, some of the time a nanotube really can look like that the surface has no contaminants whatsoever that you can see through an electron microscope. And that, I think, is a fantastic tool to have. Apart from that, the other advantages of using a nanotube rather than using some other kind of mechanical resonator is because they're so light, they have a high frequency, which means that you ought to be able to cool them to their ground state using a dilution refrigerator. We haven't tested that yet, but it ought to be true, assuming they equilibrate. The quality factor is high, like I said, over 1 million often. The spring constant is small, which means that the 0 point amplitude is large, and it loves making contact with metal, so you can use it as a semiconductor and as a Josephson element in an electrical circuit as well. So these are very versatile devices. Okay, how do we make them? I'll summarize this pretty quickly. You can ask me more later if you want to know. So they're grown chemically. The process that we use is called stamping, and it works like this. You take a quartz chip with some pillars on it, and you deposit catalyst on the tops of those pillars, and then you slide the chip into a furnace, and you flow a mixture of methane and hydrogen over it and heat it to about 900 degrees. And if you've chosen the right catalyst, then the methane gets cracked, the carbon gets deposited, and some of it gets deposited in the form of nanotubes that grow away from the catalyst sites. And so these, because they're grown chemically, you can hope that they're fairly clean. And what you find is that some of them, they grow randomly, but some of them will span from one pillar to the neighboring pillar. And then to make those into devices, we take a second chip on which we have fabricated metallic contacts and gates. We align them using a mask aligner. We can't see the nanotube, but we can see the pillars. And then by bringing them together, some of the time, if there's a nanotube there, then it will stick. And we can locate those devices by measuring the electrical conductance from one side to the other. If there's some conductance there, then probably there is a nanotube as well. So this is a fairly low yield process, but it's not particularly hard to make many devices on one chip, so a couple of hundred, and find the one or two where there really is a nanotube, and then we can cool those down and find out whether they vibrate in the way that they should. So this is what the device looks like. This is a fairly large scale optical image, so it's about 1 millimeter across. If you zoom in, then you can see the nanotube is living between the pillars here, and then here is an electron microscope of a nanotube that's been fabricated by this stamping process. So we take these chips, we locate the nanotubes, we measure them inside a dilution refrigerator at a temperature of around 20 millikelvin. So here, this is so on the right here, this is our dilution refrigerator, which is wired with electronics that allows us to send in high frequency signals and also to measure at high frequency as well. So we have DC, radio frequency, and microwave electronics all inside the fridge. The coldest part of the fridge is the bottom part, and that's where the nanotube lives. So we put the chip containing the vibrating nanotube in the middle of a circuit board. The circuit board contains other electronics that we use to measure it. This goes inside a sample holder, and the sample holder mates with the electronics inside the fridge. And then we cool it down. Okay, so the first thing that we need to be able to do is to measure the nanotube's motion, and therefore the force, electrically. And what we're looking for then is we want to arrange things so that the current through the nanotube depends very steeply on the electrical potential. So in other words, we want to make a kind of transistor here. So a transistor is a device where the current is controlled by the electrical potential in the channel. This is exactly the situation that we want here. So what you have if you apply a voltage to the gates here, there's an electric field, and when the nanotube moves in that field by vibrating up or down, then the electrical potential on the middle part of it changes. And so if we have arranged things so that there's this strong dependence here, then the current will change, and we can measure that. So when there's a large current, we know it's displaced upwards. When there's a small current, then we know it's displaced downwards. And the way that we achieve this steep dependence is that we realize a single electron transistor. We create a single electron transistor in the middle part of the nanotube. So this is how we do it. We adjust the gate voltages so that the two ends of the nanotube are undoped, but the middle part is doped. So an electron that wants to go from one side to the other has to tunnel through the first barrier, has to live on the central part, the island, for a while, and then has to tunnel out. And when it's in here, of course, then it's confined by the fact that there's a tunnel barrier on each side. And the current through such a device varies, it oscillates as a function of the gate voltage. And the reason is that the central part here, the island, behaves something like an artificial atom because it has a charging energy. Then there is a ladder of energy levels. When you change the potential on the island, which you can do by changing the gate voltage, then this entire ladder of levels moves up or down. And if when you apply a bias, then what you're doing is you're opening a window between the source and the drain contacts, in which through which an electron, which has an energy in that window, can move. And if there is a level between these two sides, the electron can go through. If there's no level, it can't go through, and so the current is low. So this is what we measure here. This is current as a function of gate voltage, and you can see it's oscillating up or down in exactly the way that it should. And this is called a single electron transistor because it takes a single electron to go through the entire cycle from being on to off to on again. Right, now because you only need a very small amount of charge to switch it, that means it's a very sensitive, its current depends very sensitively on the electrical potential or equivalently on the motion. So what we do is we position ourselves, we adjust the gate voltage so that the device is configured somewhere on the side or on the flank of one of these peaks here. And then when the potential changes, which can either be from the gate voltage or from the motion, then the current changes, and so we can detect that. And the big experimental challenge, as well as making the devices, is to be able to measure this pretty small current, so picoamps or less even, fast enough that you can see the oscillations. And this is how we do it. I can talk a lot more about that, or you can read these papers. We have a circuit in which we separate the DC and the radio frequency parts of current parts. So we can change the DC bias to apply a voltage across a DC voltage across the device and measure the DC current. But at the same time, we can pick out the oscillating part and amplify that using a very sensitive squid amplifier and measure it using a spectrum analyzer or an oscilloscope to see what the voltage is doing. And the upshot of this measurement is that what we measure here, the voltage that comes out of our experiment, is proportional to the displacement of the nanotube. So what we expect to see if the nanotube is moving is that this voltage here will oscillate at a particular frequency that's given by the nanotube's motion. So this is very nice because we can measure small displacements. Where it gets interesting, though, is if you think about the back action that's involved in this measurement. So what we have is, if you simplify it down to the most important parts, we have a two-level system, which is the charge state of the nanotube. So this is a two-level system because there can either be an electron on the island or the electron can be elsewhere. We can ignore states with more electrons because the temperature is very low. So this is a two-level system, and it's coupled to the mechanics because the force, because each electron on the nanotube, trapped on the nanotube, exerts a force on it as well. But it runs the other way as well, because when the nanotube moves, that changes the energy levels as well. So therefore, the tunnel rates change. So we have feedback. We have an effect in both directions. The charge state can exert a force on the resonator, and the displacement of the resonator can adjust the charge state of the island. So we have a two-level system that is coupled to a resonator, and depending on how strong the electric field is, the strength of that coupling can change. So what we want to do, if we're measuring the motion, then what we're interested in is this half of the arrow. But what we get as well, what we cannot avoid, is the other half, which is the back action, how the measurement perturbs the mechanics. And this is suggestive, I would say, of the behavior of a laser, where you have in a laser you have a cloud of defects or molecules acting as two-level systems coupled to an electromagnetic cavity. In our state, we have a single two-level system coupled to a mechanical coupling, but still there is some coupling between them that in some ways is analogous to stimulated emission. And this connection was recognized long before we did the experiment. Back in at least 2007, there were a few papers that identified this and predicted the signature of this mechanical lasing would be that even when the resonator is not being driven, it will still excite itself. So just like with a laser, as long as you're exciting the two-level system somehow, then it will emit electromagnetic radiation. With this kind of nanomechanical device, as long as you're somehow exciting the two-level system out of equilibrium, then the resonator will oscillate. And indeed, we see that. So we can adjust the coupling between the two by controlling the gate voltage. And what we find is that if we look at the signal that comes out of the experiment and we Fourier transform it to get the power spectrum, then depending exactly how we configure it, how we configure the voltages involved, then we can switch between a state where there's no emission and a state where there is emission, where there's this very bright peak, that shows that the device is going into a self-sustained oscillation at that point. And now you might ask the question, right, to what extent is this laser-like behavior, to what extent is that really quantum? And the answer, I would say, is fundamentally not at all. A laser, too, I would say, is fundamentally not quantum. There's no superposition involved. However, you can still say that it's different from just a resonator by itself. So just as a laser is different from a light bulb. So let me explain what I mean by that. If I open a book on quantum optics, then it will tell me there is a difference between the coherent emission of a laser and the incoherent emission of a light bulb. And this is something that you cannot tell just by looking at the spectrum. If I take a light bulb and I put a monochromator in front of it that lets through only some narrow band of wavelength, even though the line that gets emitted here may be just as narrow as the emission from a laser, there is still a fundamental difference between what comes out. And that difference is classical coherence, which is that the laser, as well as emitting at a fixed frequency and with a defined phase, also has a roughly fixed amplitude as well. The light bulb is a thermal source, and its amplitude fluctuates. So to distinguish between the coherent emitter and the incoherent emitter, then what you need to do is you need to separate out the cosine component and the sine component of the electric field. And if you plot those against each other, you will see the laser, they go round and round in a circle. And for an incoherent source, then you just get this chaotic thermal smudge here. So we set out to do the same experiment with our emitter. And to do that, we built a heterodyne demodulation circuit, which is an electronic circuit that separates out the cosine and the sine components. And we measured those as a function of time. And what you can see is that there's clearly some fairly stable frequency, which is what you expect. That shows that the device is vibrating at one particular frequency. But more interestingly, you can see that the amplitude stays fixed as well. And this is what we mean by coherence in the classical sense. And so it's coherent in the same way that laser light is coherent. And then to be more specific about this, we can do some statistics. So we take a long trace of this, and we can plot a histogram of the in-phase and quadrature signals, which means the cosine part and the sine part. Above threshold, we get a beautiful donut, just like a laser. Below threshold, then it's a spot, just like a thermal source. And then we can also plot the G1 and indeed the G2 of the emission as well, which is to say the autocorrelation functions. And you can see the correlation increases when you are above threshold. And the reason is that the feedback, the positive feedback, locks the oscillator to the center of its resonant frequency. So that shows that you can do lots of interesting things with a vibrating nanotube, and shows that you can get coherence in the classical sense. But of course, quantum behavior is much deeper than this. And to show that this mesoscopic object, this million nucleons or so in a nanotube is behaving in a quantum way, you need much more than this. And what you really want to show is interference between two parts. And so in the second part of my talk, then I will present a proposal how you perhaps can do that using by adding a superconducting qubit to the nanomechanical resonator. So let me very quickly summarize matter wave interferometry. So this is it's a way that you can look for anything that violates quantum mechanics, which in most cases is noise or random forces that are being exerted on your experiment, which is useful often, but sometimes it might even be something fundamental. And this has motivated an enormously sophisticated experiments to probe this with ever larger masses. What they all have in common is that you have some particle source that you pass through a diffraction grating, which has multiple paths. And when these interfere with each other, then you see an interference pattern that shows you that you can have destructive interference, that the particle really has delocalized itself. This wave function really has split in two and then recombined. And if you could do this with a macroscopic object, then that would show you that quantum mechanics really is true on that kind of scale. So I think that's, well, many people have lots of interesting ways for how to approach this. The record at the moment, I believe, comes from molecular beam experiments. I think this is the record from the Arndt group in 2019. They took a molecule that contained more than 25,000 nucleons, and then by an incredibly careful experiment in which all of the noise was controlled, then they were able to have a source of molecules, to collimate them so as to suppress their transverse motion. And then by passing them through a series of gratings, they were able to see the interference as a function of position at the detector. And well, so first of all, I should say this experiment is way ahead of us because they actually did it, first of all. But also it's extremely hard, and it gets harder the more massive the molecule is, for all kinds of reasons. One of them is that if you want to make these gratings finer, then it becomes at some point so small that the molecule is very unlikely to go through. It's going to experience some van der Waals force from the grating that breaks your experiment. They get around that by using standing optical waves as their grating, so there's no van der Waals forces there. But the challenge you have then is that the wavelength of light is only so small. So if your de Broglie wavelength, which is typically femtometers or picometers, since that's much smaller than the wavelength of light, you have to compensate for that by allowing the molecule's wave function to spread out for longer, which means you need a longer distance. And as the molecule gets bigger and bigger, that distance becomes ever longer, and the experiments get harder. So it's very interesting to think about what you might do with some tethered mechanical object, some tethered moving object, where you could, in principle, let it stay tethered for a very long period of time. You don't need a very long time in free fall. The question is, can you in any way measure interference with a tethered resonator? And in our proposal, then you should be able to. So the scheme in this is we want to do interference again. We want to realize a diffraction grating where the particle under test is the entire moving nanotube. And you have no hope of doing this, I would say, with a real physical diffraction grating, because the de Broglie wavelength of the nanotube is about a femtometer, and that's simply, there's just no way you can make a grating that's that small and push it through and push it out again. So we have to think of some other way. So we have to realize an effective grating, somewhat in the spirit of the optical grating that the Arndt group uses. And our proposal is to do that by coupling the resonator to a qubit. So here's the schematic. Imagine we have a resonator, which you can even think of as being a pendulum. So any kind of massive harmonic oscillator. That is coupled to a qubit, which is a two-level system with ground state and excited state. And then the qubit is the thing that you experimentally read out and control. Can you create a diffraction grating like that? Okay, before I answer that question, I should just say this is far from the only proposal to control mechanical quantum effects using a qubit. There are some from Gavin and others using falling diamond nanoparticles. There've also been nice experiments from the Lucan group and others using magnetic cantilevers coupled to nitrogen vacancy center qubits in diamond. None of these have yet shown quantum interference. Let me explain how we can realize a grating using a qubit, in how our proposal realizes the grating using the qubit. So what we need is, if we think about a conventional diffraction grating for a moment, then, as you know, you send a particle through some pattern of slits. And what the grating does is it gives you a probability to transmit the particle that depends on its displacement. So if you have, if you're diffracting light, for example, and you have a pattern of black and white fringes or black and white strips like this, then where it's opaque, then the particle doesn't pass through, and then where it's transparent, the particle does pass through. So you end up with a transmission probability that depends on displacement like this. Now, of course, you can't do that, as I said, for a nanotube, but what perhaps we could try to do, if we can couple the particle to a qubit in such a way that the state of the qubit depends on the displacement of the particle in this sinusoidal way. So what we need, in other words, is we prepare the qubit in its ground state, we let it interact with the particle, and then we measure it. We'll get either ground state or excited state. Supposing that the probability of the excited state depends on displacement like this, then we have something that's a bit like a diffraction grating. Because what we can say is, if we measure the excited state, then we know the particle must have been here or here or here or here, but it probably wasn't here or here or here. So what you can think of, another way of thinking about it is you collapse the state of the particle onto a state that varies with position like this. So if we find that if we let the particle interact with the qubit and we measure the excited state, then what we can say is that the probability distribution to be at position X, given that we measured the excited state of the qubit, is given by Bayes' rule and is proportional to the probability of the excited state given a certain displacement. So this is an effective diffraction grating, because if we do this operation, if we find the qubits in state E, then we know the particle must have passed through one of these places here. If we find the other state, if we find that the qubit is still in its ground state, then the simplest thing we can do is we can simply say, okay, that was a run of the experiment in which the particle hit the opaque part of the grid, so we're going to ignore those results. If you want to be more sophisticated, then you can say it passed through a different grid that has opaque and transparent inverted from each other. Okay. So this is what we're trying to do. And note, I haven't told you anything about how we realize this, this particular interaction here. But this is what I will now explain. What we need to be able to do that is strong coupling between a qubit and a mechanical resonator. So suppose that we have a qubit plus a resonator. We can write down the Hamiltonian for that. The qubit's a two-level system, so its Hamiltonian is simply sigma z with a prefactor that's set by its frequency. The resonator is a harmonic oscillator that gives us an A dagger A. And then there is a coupling between them, which says that the qubit energy splitting, this omega q, needs to depend on displacement, displacement x. So what you have is you have a little a position-dependent change in the energy splitting of the qubit. So as the resonator vibrates backwards and forwards, the energy spacing of the qubit is going to be vibrating upwards and downwards like this. And if the resonator is moving slowly enough, then you can say even that the qubit energy splitting simply depends on its displacement. So if we can create a device with this Hamiltonian, then we can realize the effective diffraction grating. And it works like this. We prepare the qubit in its ground state. Then we apply a qubit rotation, a pi over 2 pulse, that brings the qubit down to the equator of its Bloch sphere. And then we let it process. And it will process at a rate that's proportional to, well, the rate that depends on the instantaneous qubit splitting omega q. So when x is 0, when the resonator is at its equilibrium position, then the qubit doesn't process at all. But if x is displaced, then the qubit processes one way or another. So it'll go round and round for some amount of time, however long we wait for, at a rate proportional to the displacement. And then at the end of that, then we apply another pulse that brings it back, and then we measure it. And what we find is that the probability to come back to where we started is proportional to the cosine of how long we've waited for, or alternatively to the cosine of the displacement. So if the wave function of the particle before we did this is given by this Gaussian, so the ground state of the harmonic oscillator, after we apply the sequence, then it gets conditional on the outcome of that sequence. The wave function gets multiplied by the cosine, by the cos squared, and so we get this these fringes in the wave function that's equivalent to the particle passing through a grid. So that's the effective diffraction grating. And to measure interference, we simply have to do this 3 times. So this is a simulation of how it works. Here's the initial wave function. We imagine the resonator starts off in its ground state. We do the first sequence. We condition on the outcome to generate a superposition. The particle's wave function then splits into 2 branches. Because of the restoring force, because it's a clamped resonator, those 2 branches at some point will start to come back towards each other. But at the point when they're furthest apart, then we apply a second grating, and then we apply a third grating to measure it. And what you can see is that the effect of splitting and then recombining the wave function is to give you interference fringes in the middle of the pattern here. And those interference fringes will appear, if they exist, they will appear in the outcome of the qubit measurement that comes from the third grating. Another way you can look at it is you can say the probability of passing this grating depends on the alignment of the grating with the interference fringes. Okay, that's all very well to write down Hamiltonians and simulate them, but do we have a hope of actually making this device? And I think we do have a hope. We haven't done it yet, but I can show you how we think it ought to work. What we want to do is to start with a really excellent qubit, which is the superconducting transmon qubit. So this is the workhorse of quantum computing at Google and IBM and many other places. So there's been an enormous amount of work on these devices. What you have to make a transmon is it's an LC resonator. You have a capacitor and you have an inductor, but the inductor is realized by a superconducting Josephson inductance. And so this is a resonator and its frequency is 1 over root LC. The reason that you have to use a Josephson inductance here is because it's slightly nonlinear, which means that the ladder of levels that you get for an LC resonator boils down to, in the end, just 2 that you care about, which are the 2 qubit states. Okay, so that's a transmon, and normally this Josephson inductance is realized by using an aluminium oxide junction. So these things have fantastic coherence times, beautiful fidelities, but there's no mechanics in them yet. So we set out to modify this design, and the first thing we did was to introduce a squid into it. So this is a flux tunable transmon, which is also something that exists. And what we have done here is we have separated out the 2 sides of the circuit. So you have a square on top and a square on the bottom. This is completely standard. And then this Josephson junction here has become 2 Josephson junctions with a flux between them. And the reason to have the flux is that it lets you tune the inductance according to this formula here. As you change the magnetic field, the inductance changes and therefore the qubit frequency changes. Okay, that's still not enough. We did an extra step, which is that we imagined that we had a concentric transform. So what we've done here is to take this bottom electrode and make it into a ring, so it goes around the outside. And the reason that we do that is that this outermost ring here protects the flux here from static or from global magnetic fluxes, and therefore makes the qubit more immune to noise. And then as a last step, we introduce the mechanics by moving these two junctions up, and then by making one of them something that vibrates. So now the energy levels of this qubit are still given by this fundamental formula here. The inductance is still affected by magnetic flux, as in this formula here. But what it cares about is the difference in flux between the two sides of the two areas enclosed by the qubit. And so if this part is moving, then when it moves one way, the flux increases. When it moves the other way, the flux decreases. And so we find that the qubit frequency depends on flux in the way that we want. So that in principle is how it works. The really big question is, can you get a coupling that is strong enough to let you see quantum effects, even knowing that the qubit has a finite lifetime, that the mechanics has a finite lifetime, that everything's at a finite temperature? And that's a much harder question. But we have simulated it. So this is our device. This is our formula for how the qubit frequency depends on the position. It's governed by an in-plane magnetic field. So what you have to imagine is that the resonator is moving towards you or away from you. And if we do that, then the qubit frequency depends on the flux in this very steep way here. If you're sitting on one side of this steep dependence, then a small change in flux, either because of an external magnetic field or because there's a change in the device's displacement, gives you a change in the qubit frequency and therefore a coupling. Okay. That's how it works in principle. So in principle, it certainly works. All the ingredients are there. Is it practical? Well, that depends on the parameters. So in our paper where we proposed this, we sketched out a device that has parameters that come from previous experiments. And what we reckoned is that with a nanotube 800 nanometers long, so that's about 3 million nuclei, then if you make assumptions that are perhaps not too crazy with regard to the qubit lifetime and the magnetic field, that you should be able to get a coupling constant that's strong enough to realize this experiment. And that would be fantastic because, of course, 10 million AMU is about 100 times larger. Sorry, 3 million AMU is about 100 times larger than any experiments with a molecular beam interference so far. And in our paper, then we go into some detail about how exactly you recognize the interference and how you distinguish them from classical effects, such as the shadow of the resonator. And the upshot is that even if there's some decoherence, you should still be able to see fringes that are quite different from what you expect classically. And you see those by measuring the qubit after the final step. So that's the theory. We have taken some steps towards trying to realize this in collaboration with the Peter Leak group in Oxford. So we had a joint student called Matthias Mergenthaler who did an experiment in which he did not worry about any mechanics and he did not worry about making an ultra clean device, but he simply asked the question, can you make a qubit, a superconducting qubit, in which the Drussison junction is a nanotube? And the answer is yes. So here's a picture of the device. What you can see here is a zoom in at the junction. So the qubit looks something like this. These are the two sides of it that are capacitively coupled. This is the Drussison junction, and there's a control gate that let him adjust the energy. And he found that there was a qubit and measured its lifetime as well, which is still in this not super clean device was not particularly long, and so far not long enough to do the experiment. But what I hope is that by suspending the device, by paying more attention to the clean fabrication, that we can extend the coherence time and have some chance of detecting motion and ultimately interference by measuring the qubit. So to summarize, these are the two things I talked about. I talked about classical coherence, also known as the phonon laser, by making fast and sensitive measurements of a oscillating nanotube. And then I presented our proposal for matter wave interferometry using a qubit as well. Thank you for your attention.
Great stuff. That was really exciting, Edward. Thank you very much. I've got millions of questions, but unfortunately I'm the chair, so I have to ask if anyone else wants to ask any questions first. So you can put your hand up, you can write stuff in the chat, you can unmute yourself and turn on your video to ask questions. Oh yeah, Miles, go ahead.
Thank you for the really fascinating talk. I just have two short questions, I think. So the first one is, in the single electron transistor device, did the electrons tunnel incoherently on and off the island in your acoustic laser setup? Just thinking about
what exactly do you mean by incoherently in this sense?
Well, so you know, it's like how should I describe it? Like a shot, you produce a shot noise, and the electrons tunnel on to the island and off. It's an incoherent process that you can model with a rate equation or something, versus the coherent tunneling process. For example, you know, if you had Cooper pairs that form a supercurrent, just as a kind of contrasting, a very coherent device.
Well, so there's no Cooper pairs. There's no superconductivity.
Yeah, of course. Yeah. It's a normal current.
Yeah, I think we are able to reproduce the behavior qualitatively using a rate equation. So I think it's incoherent in that sense. All you care about is the average number of electrons on the island.
I see.
For the function of the position.
Okay. And then my other question was in your second device. I'm just making sure I understood it correctly. So your tunnel junction, also one of the tunnel junctions is actually the nanotube.
Yes,
is that right?
That's the plan.
Is that essential? I mean, can it also work if the tunnel junction was fixed?
Oh yes.
And the nanotube was just forming part of the closed loop, so that you're still changing the flux. So I mean, why do the two have to be the same?
We imagined that it would be simpler. I mean, in fact, you don't even need a nanotube at all. You could have a vibrating piece of aluminium.
Yes.
The nice thing about a nanotube is the zero. Well, it has two benefits. The 0 point amplitude is large, and the thermal occupancy is small. And then, since it can act as a Josephson junction, that's quite a convenient thing to do.
Okay, thank you.
Isaac, yeah, go ahead.
Hi, thanks for the talk.
Thank you.
I guess I have this question about the so with this oscillator coupled to the qubit. I guess like if you to like be measuring this, I guess my question is like, if you're measuring this oscillator, presumably it can't form superpositions, which is what you need with the qubit. And so have you looked at what kind of evolution it would look like if you were forming the, I guess I'm thinking in the optical context, it'd be like a heterodyne measurement or something with this.
Yes.
In the sense that if you're measuring
so you're talking about nanotube coupled to qubits.
Yeah, exactly.
Yes, we haven't modeled it, and I'm sure that yeah, I mean, it's crucial that you don't look at it while it's evolving between the diffraction gratings. So yeah, you have to make sure that the whole experiment is well enough controlled that that doesn't happen. Does that answer your question?
I guess I guess you might think that like there are regimes in which this oscillator, this nanotube will look classical, and which it won't look classical. And I guess I'm a bit confused. Presumably to generate these superpositions, we need it not to be classical.
Presumably, yes.
So it can form these superpositions, or with the qubit. So I guess I'm just interested in like if you've looked at or modeled what it would look like in the kind of classical regime, or where it's been continuously measured or something like this.
Not really. What we did in the paper was to simulate added phonons between the gratings. So this could, for example, come from the hot environment.
Right. Okay. Yeah.
And that indeed washes out the fringes.
Okay. Cool. Thank you.
Hi,
Ed.
Ed.
Oh, sorry. Could I ask a question, Ed?
Yeah.
Oh, I just don't have a hand.
Hi, Ed. Yes.
I haven't got a hand to put up. I don't. Maybe I'm not in the right group. I have two questions. The first is: are these single mode vibrations of these nanotubes? I mean, when you play a musical instrument, you get several modes. And
yes. Yeah, you're not driving it hard enough that it becomes really nonlinear, I think.
And then the other thing I didn't understand is, do you have to take into account if you've got this vibrating nanotube in a field and it's carrying a current, is there a F equal BIL? Is that factored in? Because that's a slightly different situation to the way you started to describe it, where it's controlled just by gates applying forces.
Yes, the magnetic force is much smaller than the electrostatic force for these devices, because, for the reason that the current, they're not very conductive, so the current is not very large. And then inside the qubit, of course, then I suppose what you have is a persistent current. So so presumably then there's some kind of DC force that shifts the equilibrium position.
Yeah, I can't work it out. It's like if you've got if B is static.
Yes.
And then I is at some frequency.
Yes.
But you're not applying an AC signal to you're letting there's nothing. Once it started vibrating, are you continually driving the wire?
No, in neither experiment.
Okay.
Not in the experiment nor in the proposal. So it's evolving just under the influence of, if you're talking about the qubit experiment, it's evolving just under the influence of the qubit coupling.
Yeah. Okay, that's my question. Sorry for interrupting there, Sugata. I think you were trying to ask something.
Hi, Ed. Hi. Very, very interesting talk. I'm going to ask you a question which I probably have asked you a couple of years ago. So please pardon if you say that. So when you have this two-level atom, right? Then or the superconducting qubit. So like in your picture in that grating thing, so it splits to two parts, right? With the two-level system. So this is what the multiple splitting. Do you have to use the qubit multiple times to get to multiple splitting? I mean, from the logic that you gave, initially it seemed like you could split to multiple, with different x's having the same excited state. But the way I understand this Hamiltonian, it is one of the state pushes one way and the other pushes the other way. So for multiple things, what do you do?
You're asking how we get the three-part diffraction grating, or are you saying can you make even more grating?
Multiple. So the picture that you have shown, this multiple peak superposition. Do you get the multiple peak superposition from just one grating?
Oh, I think you must do, because it's it's periodic. So so yes, it must come back as fringes, because sorry, let me go to the picture again. Yes, if it starts off here, then after one period it must have the same distribution. So presumably you get fringes there. We haven't simulated Yeah, it's a good question, actually. Whether,
Hmm.
well, okay, yeah, but that I would say is not quantum interference, because all that's saying is when you go through a grating, even classically, you see the shadow of that grating. So the fact that it comes back is just because you have the shadow that moves apart and then comes back to the origin.
I see. Okay, and this, when you say grating 1, grating 2, grating 3, you are going to reuse your superconducting same qubit 3 times,
yes.
or okay. Okay. I think I try to start to understand that. Yeah. And did you say something in the talk about the size of your carbon nanotube mass, the largest you can have and the largest splitting you can have?
Yes, it's about 3 million AMU.
Okay, that's quite a lot. Yeah, and what is the largest splitting you can get?
The largest splitting in space.
Yeah, like the separation, the superposed components.
Well, let's see. So the width of this
the ground
wave
state
function
is within
is the 0 point.
I see. It's all within that, is it?
Well, you can see it's a couple of times the 0 point amplitude.
Right,
so
right.
So that's it's of order 1 picometer. So it's going to be something like 4 picometer splitting. So much less than the diameter of the nanotube.
Okay. Thanks very much. Yeah.
Jessica, go ahead.
I have a question about the kind of operation where you pulse the qubit into superposition and it processes and you pulse it back. I was wondering if you use like the electrical gates to do that, and does that then not set the resonator kind of resonating at a different frequency if you pulse it back? How does that interfere with the measurement?
In principle, it ought not to, because the way that you control these qubits is by driving them at the qubit frequency, which is very far away from the mechanical resonator frequency.
Okay.
So that part I am not particularly worried about.
Okay.
Okay. Do I get to ask some of my questions now, or anyone else with questions? So let me ask, maybe could you go to slide 41? So this is just, this is just perhaps a stupid question, but how does it work with the flux that's in there when the nanotube moves? Do you effectively have the same amount of flux in there and it gets concentrated a bit when the nanotube moves up? Or is that not the right way to think about it? Or does the flux?
No, I would think about it as the nanotube is cutting flux lines.
Okay.
Which it can do because it's a junction, obviously not a pure piece of superconductor.
Exactly. Okay, I see. Yeah. Okay. Makes sense. Great. And then an obvious sort of a question that other people like Sagatu here might wonder is, what would happen if you had 2 of your nanotubes next to each other? Could you look for this sort of gravitational entanglement that we've talked about? I mean, I think you've got very small superposition distance, and so maybe it seems implausible, but maybe, what if you measured for a year? I don't know, would you be able to build up slowly?
That's a great, really interesting question. I'm not sure I can say anything very interesting about it. But yeah, I mean, I suppose one advantage of nanofabricated resonators is you can put 2 of them extremely close together. I mean, you can etch, if you're willing to etch a gap in some superconductor, you can etch a gap that's 50 nanometers wide. So I just think that's yeah, you're right. Maybe that's an advantage compared with levitated particles.
Yeah, and maybe if you had in your dilution fridge, I don't know, you might have room for 1,000 or 100,000 devices. Maybe you're collecting some minuscule amount of information per device per second, but maybe in a year with a million devices, then you get a lot of information out. I haven't thought about it. I don't know.
Great question.
So I was in this context, I was a bit surprised that it's a nanotube, and still 6 million AMU is is less than the nanocrystals. Is that? It's still quite a light object.
Well,
yeah,
I mean, it's light and it's hollow, I suppose.
Ah, I see.
And it's thin, of course.
So, Edward, I have a question. So, can you make a very, very long nanotube? How long can you make it in a superposition? What will be the length?
How long can we make it?
Yeah. I mean,
we could. You can grow them. I mean, so the real material science experts grow them centimeters long. However, if you want to couple it to a qubit, then an important problem is the superconducting. It has to be proximatized. So the superconducting wave function will spill in by roughly 1 coherence length. Okay. So that limits you to a few hundred nanometers.
Nice. And so if I understand, so these nanotubes are very thin. So what's the radius of these nanotubes? So my very dumb question would be, can I imagine them to be some kind of like a string?
You certainly can imagine them to be a string. The radius for a single wall nanotube is about 2 nanometers.
Roughly 2 nanometers. And you can say that you're saying that you can grow it up to centimeters long. Oh,
if you're good, yes.
Superposition. Is it possible, or is it viable at all?
Yeah, I mean, good question. You have to find some other way to couple it to a qubit, though. You couldn't do it with a superconducting qubit for the reason I just said. Mm-hmm. But whether you could have one inside an optical cavity, maybe. Mm-hmm. I don't know.
Okay. Now, why I asked this question, because then you can treat them as like a cosmic strings in your lab, given the fact that you can create a superposition roughly around, say, I don't know, it's a nanometer, but if you can somehow make it slightly more bigger split, maybe roughly of the order of micrometer, given the fact that the sizes of these objects are nanometer, or the radius, it might be interesting. It might have some interesting application, if it's at all possible. I don't know. I mean, what are the constraints?
I need to think very carefully about what the constraints are. Yeah. So do you say for detecting cosmic strings, or for acting as a model of what?
So the very interesting property is that if you take a very long string,
yes,
3 + 1 dimensions, they don't generate any gravitational potential. It's because the way you create a cosmic strings is that you take a plain sheet of paper, you cut your deficit angle. Suppose I cut a small angular part from the sheet, and I take the tip of that and just spread it all the way from +∞ to -∞. That becomes my cosmic strings. But the fact that I created the cosmic strings from a plain sheet of paper, which doesn't have any curvature, it signifies that a cosmic string as such does not gravitate at the lowest level. Of course, it does gravitate, but at a higher order in G. So that's why I was curious to know that if one can build such a device, put it in superposition, then you would not see any gravitational entanglement at the lowest order. And the next order would be so weak that we will never be able to, see it in a laboratory, its effect. But at the lowest order, you will not see the prominent interaction. Would be maybe Casimir or something sort of that. So it might be interesting from this perspective.
Okay, but this is not a property of all strings. It's a property particularly of cosmic strings.
Yeah, it's very long string. I mean, you have to very, very long strings. And so suppose you want to do exactly like what Gavin was asking, that you want to do similar experiment, you would see that even if you make them heavy enough, as long as they're sufficiently long, they would not gravitate at lowest order in G. So that's an interesting property.
I don't understand that, Anupam.
That's right.
Yeah, it's a very interesting property. So one way to imagine is that the way you create a maybe let me take a piece of paper, but imagine I have a book and it's a sheet. And the way I create cosmic string is that I cut it from here and here. I take away this part of the paper, let's say. I take the tip and I stretch it all the way to plus infinity and minus infinity. That becomes my cosmic string. So cosmic strings are created because of the defect. It's not really, so it's kind of like a defect. The defect becomes the deficit angle. So, so the fact that in 3+1 dimension, the sheet doesn't have any curvature, and if you create a cosmic string through this way, you do not exert any gravitational potential. So the string does not exert any gravitational potential at the lowest order in G. It does give you, it does gravitate, but it gravitates with effects like a G square, not at G. So that's the advantage, that if you create a superposition with cosmic strings, at the lowest order, you will not entangle things due to gravity. You can entangle via Casimir or some other interactions.
But the nanotube, made from real massive carbon atoms, presumably gravitates.
That's why I was asking you the question: how thin can you make it in a laboratory, and how long? So in that approximation, I can treat it. So if I'm looking at, say, micrometer distance, but my size is a meter, let's say, just to give an example here, of course, making it meter is very hard. Then maybe if, for sufficiently close distance, you can treat them like a string, cosmic string.
Okay, well, thank you.
Nice.
Yeah, I'm going to go read about cosmic strings afterwards. I've got another question, Edward. What about there's this work from O'Connell in 2010 and Teufel and Silanpa, and so how would the massive superposition that you generate compare to the experiments that those people have done?
The mass would be much less. It's, I would say, a different kind of superposition. In O'Connell's experiment, he had a piezoelectric resonator that was doing a breathing mode, so its center of mass was not moving. In the other two papers that you mentioned, they both work with aluminium drums, which do have a center of mass motion. And in fact, they even measure entanglement between two separate drums. So if your two drums are either both doing this, they're either both doing this, or they're both doing that, but they're not doing this. And that's not the same as interference. I mean, I would say it's still evidence of, almost certain evidence of entanglement. Sorry, almost certain evidence of superposition. If you have entanglement, you must have superposition. But what I don't understand is whether that kind of entanglement experiment is as good a test of quantum superposition as an interference experiment is, because there's no two paths involved. Perhaps one of the theorists on the call might even be able to tell us. Okay, well, I don't know the answer, but it is something different, definitely.
I mean, they have not really done a superposition, right? They have cooled to the ground state and done two-mode squeezing type of things, right?
Yes, is that?
They have entangled two oscillators like this.
Mm-hmm.
Some of them are just.
Yeah.
But is that the test you need? I mean, if you could entangle two oscillators that both have the Planck mass, have you then shown that gravitational collapse doesn't exist?
No, I'm not talking in context of gravity. No, I'm just telling that these other people have entangled, just using a beam splitter interaction oscillators. So that is possible. Difficult. I mean, if you just want to prove the quantumness of something, then probably you don't always have to create full large-scale superpositions. On the other hand, I think I don't think they have proved this. They haven't produced this kind of non-Gaussian states that you're planning to produce, right? Collection. Now,
okay.
one thing which your state reminds me is very similar to this GKP state. The kind of state in which Gottesman, Preskel, Kitaev had this coding. Like one of those where the zero logical and a slightly shifted one was the one logical. these were exactly like your grating states, like a bomb kind of thing inside an oscillator.
Okay, that's
So
interesting.
Yeah.
And
so I
how do
wonder
they
whether-
envisage creating those?
That I don't remember at all. Yeah, I mean, so have a look at the papers. I mean, in their original paper, whether they even proposed a way to create, I don't know. But people have lots of papers on that, so there should be. And
Thank
maybe
you.
creation will involve something like this, as you said. I don't know whether they're exactly your states, but it's a bit like dividing up an oscillator ground state into alternate parts of amplitudes.
That sounds a lot like what we simulated.
Yeah, exactly. Yeah, your version and site the displaced one of yours, the complementary one, would be the two logical states apparently. So you can check that up, literature up. I'm not fully remember exactly.
So Sugata, are you saying that the demonstrations from these people of entanglement, that doesn't rule out objective collapse, I guess, because you don't have a macroscopic.
Their entanglement is.
They're not done a macroscopic superposition. I thought that.
Did they do anyone?
Not macroscopic, but I thought they did. Have they not done a superposition of?
I think they have superposed vibrational states like 0 and 1. They may. Yeah. Okay. So that was your question. No. Yeah. So there is some degree of superposition in one of the states. If they have made a 0 plus 1, some atoms are displaced. Yeah.
Yeah, I think they have, right?
Mm-hmm.
Is that right, Edward? They've made a superposition of sort of a 0 phonon plus 1 phonon.
Yes.
Yeah.
Yes. Of this center of this breathing mode. Yeah.
Yeah. But so they haven't done it for the sort of the drum that actually has a moving center of mass.
As far as I know, they haven't. I mean, it seems to be easier to do entanglement than to do superposition, which is surprising.
Yeah. Well, yeah, interesting. Lots of interesting stuff here. Maybe we should wrap it up there. I think don't see any more questions. That's been fascinating. Thanks very much, Edward. And
thank you. Yeah, and thank you for the great discussion as well. I mean, it actually works pretty well online. It's much easier than going down to Warwick and talking to all of us.
Yeah, it's surprising sometimes. Yeah.
Now, also people from everywhere can join, right? Like Miles joined.
Well, I feel being in a room, you could have more spontaneous discussions and talk on top of each other. Don't feel so comfortable, but it was a wonderful talk. Good luck.
Thank you.
Very inspiring.
Yeah.
Thank you.
Well, wonderful stuff.
Bye, Ed.
Right.
Okay, bye.
Let's say goodbye then and leave it there. Thanks, and